using the average rate of change to determine concavity, which is where we're going now to that, and then we'll get to the linear equation for consecutive equal length input intervals next class. Okay, so looking on the front top, it says in the previous lesson, oops, I'm frozen, you looked at rates of change from multiple representations, right? We looked at rates of changes of graphs, equations, tables, and verbal descriptions. Today we're going to consider just rates of change of linear and quadratic functions. So remember we talked about secant lines from geometry. So a secant line in this case is we're going to be talking about a line joining 2 points on a function. If I can find the slope of the secant line, which we know how to do that very easily, it's going to give us the average rate of change over any interval from A to B. Okay, so we've been doing this before. Average rate of change is just our change of y over change of our x of the slope of the secant line. That's what that subscript's talking about. And then we've seen this notation already. F of b minus f of a all over b minus a. So again, nothing new. Now we're just adding in the idea of having that secant line. So for example 1, here we have a linear graph that passes at the point 0, negative 3, and 4, 3. So explain how you know its equation is y equals 3 halves x. Is that a minus 3? Minus 3. How do we know that that's the equation? Where'd the 3 halves come from in the equation? Good. So the slope of the linear function is always 3 halves, and it crosses the y-axis at, what is it, negative 3, which is the b value in y equals mx plus b. Right, so the slope of the linear function is always 3 halves, no matter where it lies. It crosses the y-axis at negative 3, which is our b value in our slope-intercept form. So for part B, what do we notice about the average rate of change for the linear function? Is the rate of change changing anywhere? Nope, so it's constant, right? It's constant the whole entire time. Stays 3 halves the whole linear function. So the slope goes unchanged, it's constant. So for part C, how is the average rate of change related to the equation itself? Well, I'd say something to the effect of for every change in x, the y value increases by 3 halves. I mean, that's our true definition of slope. As every increase of x, your y value will increase or decrease by whatever the slope is. So for part D, if we use the grid at the right to sketch a graph of the function that represents the average rates of change of the linear function, what did we say the average rate of change of the function was? Well, it's constant, but constant at what value? 0 would be the slope of it, but it's constant at 3 halves the whole entire time, right? So we're going to make some type of horizontal line at 1.5. The slope of that line will be 0, right? So let's write out why we did that. So our average rate of change is equal to 3 halves. So y equals 1.5 will be a linear equation that represents the constant rate of change. On the function. Okay, so it's just staying 3 halves the whole time. So at time -4, what's the rate of change? -4 at at 1.5. At negative 3, what's the average rate of change? 1.5. At negative 2, what is it? 1.5. At negative 1, what is it? 1.5. Right, just stays 1.5 the whole entire time. Okay, example 2. Here we have a table for the graph. So we have the quadratic now. So now we're moving from linear to quadratic. Our quadratic function is y equals x squared minus 6x plus 5, which is graphed over here for us. That's nice. Here we have a table of values, and we want to find the average rates of change on the consecutive equal length intervals. So if we're going from 0 to 1, my average rate of change is going to be what? 5 minus 0, which is 5 over negative 1, so negative 5. From 1 to 2, 0 minus negative 3 is 3 over negative 1, so negative 3. From 2 to 3, negative 3 plus 4 is 1 over negative 1, so negative 1. From 3 to 4, negative 4 plus 3 is negative 1 over negative 1 is positive 1. 4 to 5, negative 3 minus 0 is negative 3, divided by negative 1 is positive 3, and then 0 minus 5, negative 5, divided by negative 1 is positive 5. Okay, so now using these results from the table, do we notice a pattern within these changes of rates? What's happening each time? We're going by 2. We're doing a plus 2, plus 2, plus 2, plus 2, plus 2 each time. Good. So let's write that out. So as the intervals move right, the rates increase by a factor of 2. Okay, so second question. What can you say about the rate of change at x equals 3? What's happening there at x equals 3? It's a turning point, which means our rate of change is going to be 0. Good. So at x equals 3, it's a turning point. So the rate of change is 0. Okay, nice. So we can find average rate of change within intervals. And now we're kind of looking for patterns that's happening between those intervals for our average rate of change. We all know that at a turning point, our rate of change is 0, because the tangent line is going to be that horizontal line. Okay, so let's sum this up. So over any length input value interval, the average rate of change for a linear function will always, always, always be constant, right? If it's linear, your rate of change will always be constant. The slope will be the slope no matter where you are. So it's unchanged, it's constant. Number 2, given consecutive equal length input value intervals, the average rate of change of a function of a quadratic function can then be given by a linear function, right? Because you're going to get all those linear tangents kind of bordering around our curve. And then 3, the average rate of change over the closed interval a to b is the slope of the secant line. Right? So it's that line connecting your 2 points of A and B. Find the slope of that line, and then you've got the average rate of change over the interval. Okay, example 3, concavity. So let's tie this to our concavity. In a quadratic function, we can determine the curvature or concavity of a graph by considering the average rate of change over equal length x intervals. So what we're going to do is we're going to sketch a bunch of secant lines on the graphs shown below. So if we wanted to find the slope of an increasing, I don't think this is supposed to say secant. I think that's supposed to be tangent. Change that. I don't know why we'd be finding the slopes of the secants. So if we make a tangent line here, right? My slope is, we talked about this before when we were moving our rulers around. Right now my slope is negative. If I make a tangent line here, what's happening? My slope is becoming positive, getting even more positive, getting even more positive, right? So our slopes are increasing. Over here, for concavity down, I have a positive slope. Now I went to a negative slope. Now I'm going more negative, so our slope is going to be decreasing for our concavity. And we did this before when we were doing our ruler work. Okay? All right, so last two examples, let's tie this all together. So using the function from example 2, which was our quadratic, let's consider what the graph of the average rate of change of this quadratic function would look like. So part A, the parabola is concave up. Flip back and look at 2. Yep, it was concave up, right? It was positive. Because the average rate of change on the equal length intervals is it increasing or decreasing if my average rate of change is concave up? Increasing, good. And it was increasing by a factor of, what was it, 2? All right, so we're going to call that the slope of the new function. Part B. We would also observe that the quadratic function changes from decreasing to increasing at the vertex. Where was our vertex? At x equals, what was it, 3, I think? Is that what it was? 3 is where it bottomed out. Okay, so our rate of change there is 0. We're going to say that the slope is constant. So we can use ordered pairs as our x value and our rate of change for a point somewhere on the graph. Okay, so for part C, using our results from what we just put up there, so we're going to write an equation for a linear equation to represent the average rate of change of the quadratic, and then graph the function in the grid provided. Okay, so if we said that our rate of change is changing by 2 each time, there's our new slope. And then we're going to make an ordered pair of x, comma, and our y is going to be whatever our rate is. So let's do it at 3, and the rate at 3 was 0. The reason why we're picking 3, 0 is because 0 is a nice number. Could I have used any of those other ones? I could have. I could have done, we didn't have an x value at the other. Nope, we didn't have. So 3 is the only one we had an actual 0, right? Because the other ones were in intervals. So 3, 0. So can we write the equation of that line? Hopefully. Y minus my y, so y minus 0 equals my slope of 2 times x minus my x, which is 3. So we get y equals 2x minus 6. That's your answer there. Can we graph it? Yep, start at -6, up 2 over 1. Throw a few dots in there until you feel confident about making a straight line. Or use a ruler. And there's our line. Okay, so there is the graph of our average rate of change. So what does this mean? So let's think about this. It's a linear line, yes. Has a y-intercept of -6, has a constant slope of 2. So because it's a quadratic, our average rate of changes were increasing by a rate of 2 each time, right? Which makes sense because in your quadratic, it's going to start getting really steep as you get higher up, okay? At this point at 3, what happened between my slopes from the left to the right of 3? To the left of 3, my slopes were negative. To the right of 3, my slopes were positive. So does that make sense that my linear line is positive above 3, negative below 3? We're working left to right. Okay, so this is kind of talking about our rate of changes. So my rate of change below 3 or to the left of 3 would be negative slopes, which makes sense because we were concave up. So we're negative on the left side because our equation was decreasing. And then on the right side, our equation was increasing. Yeah? We're good with that? Yep. Okay. All right, and last example, example 5. Oh, perfect, we can get this in. Of course, my internet's gonna die on me. Oh, there we go. Okay, so let's generalize the procedure for finding the average rate of change to any function on an interval. So we're gonna try to find that velocity. So we have capital F. So function F is equal to x squared plus 2. Find the average rate of change from 2 to 4. Okay, we're pros at this. Here we go. We can all do this. So our average rate of change is going to be equal to, I'm going to do 4 first, big F of 4 minus big F of 2 divided by 4 minus 2. Are we all okay with me going right to it? Gets us 12 divided by 2, which is 6. Okay, so we are professionals at finding average rate of change between an interval. Here our interval is from 2 to 4. For part B, we want to find the average range of change. So now we're going to make like a generalized formula from 2 to 2 plus h. So average rate of change, f of 2 plus h minus f of 2 all over 2 plus h minus 2. All right, well, I got to do some math. I got to plug this in. So squaring 2 plus h, squaring the 2 gets me 4. 2 times h is 2h times 2 is 4h. Squaring the h gets me h squared. And then we need a plus 2 yet. Okay, so I just evaluated 2 plus h into our formula and got that. And then evaluating it for 2, what did I say 2 was before? It was 6, so we're going to do a minus 6 all over. My 2's cancel out my denominators, which leave me with h. So now I just need to simplify that. So we have an h squared. We have a 4h. 4 plus 2 is 6. Minus 6 goes away. It's at 0. Divided by h. Factor out h in your numerator. Leaves us with h plus 4. What cancels out? Our h's. So we're just left with h plus 4 as our final expression. Okay, so can we do that by writing a general formula for the average rate of change for any points? What's that going to look like? Well, it'll just be something like f of a plus h minus f of a divided by a plus h minus a. Which what would simplify in my denominator? The a's would go right away, right? So f of a plus h minus f of a all over h, which is going to be used a lot in calculus. Okay? All right, so we're going to pause there.